In the last video, we had a look at gluons and quarks and quantum chromodynamics and how it is that new quarks and antiquarks can be created in collisions. In this video, we're just going to have a look at how hadrons can decay via the strong nuclear force. The weak nuclear force is needed to decay fundamental particles, elementary particles, but composite particles, hadrons, they can decay via the strong nuclear force. So let's have a look at a few examples. Here you can see a delta++ hadron. It has 3 up quarks. No strangeness because it's a delta particle. The strong nuclear force will change the up quark from one color into another. It will do some sort of exchange. And this will be happening within this. It's not indicated very clearly here, but within this baryon, within this delta++. That gluon can decay into a quark and an antiquark pair. They have to be the same type of quark. So in this case, the gluons decayed into a down quark and an anti-down quark, or a down antiquark, should I say. And when those 5 quarks reconfigure themselves to the lowest energy state, you end up with a proton, up, up, down, and a pi+ is emitted. So this is how a delta++ can decay via the strong nuclear force into a proton and a pion, a positive pion. Here we've got a delta+, so that is an up, down, up. Same quark composition as a proton, but it's more energetic. It can decay into a proton. The strong nuclear force means there's gluons swilling around inside this delta+ particle. One of them can decay into an up quark and an anti-up quark, which is a neutral pion. A neutral pion that's released can travel some distance and then decay itself. The previous example was a delta+. This is a delta+ as well, but this is a different possible decay. And here the up quark stays as an up quark, but because of the gluons swishing around inside there and changing colour, one of those gluons can decay into a down quark and an anti-down quark. Now the down quark can bond with the down quark and the up quark to form a neutron. That's a possible outcome of this. And that leaves the up quark and the anti-down, the down antiquark should I say, to form a positive pion. And so that's another possible way that the delta+ hadron can decay. Now, if the delta+ particle does decay this way, it's not as energetically favourable. That means this is a less likely outcome, but it's still possible. So here's a few more examples. A delta 0 decaying into a neutron. And it decays into a neutron because one of those gluons just happens to decay into an up quark and an up antiquark, the two of which form a pion. This has reduced the energy of this delta 0 particle, so it's a neutron. You'll notice the quark composition of a delta 0 and a neutron are the same, but the delta 0 is more energetic, and that extra energy can turn into mass via the strong nuclear force in creating an up and an up anti-quark. But another way that a delta 0 could decay is into a proton and a negative pion, and you can see that here. And a delta- can decay into a neutron and a negative pion, like this. Well, we started this journey with 4 elements: earth, air, fire, and water. Then we had a more complicated periodic table with about 92 elements on it. Physicists didn't like that because it was too complicated. They wanted it simpler. We went all the way down to just protons and electrons. We were happy with that, but the universe wasn't. And our current understanding of the universe has these fundamental particles that you can see listed on the bottom here. But that's not all. There are also, as I've hinted at previously, sterile neutrinos. There's some interesting physics about why neutrinos oscillate, changing flavour over longer distances. Some interesting things happen with bottom quarks. There are examples where our conservation rules seem to break down when bottom quarks appear, and maybe top quarks. And I haven't even mentioned supersymmetry yet, and other exotic particles that may or may not exist but have not yet been detected. And of course, one of the things we're hunting for is dark matter. dark matter that is responsible for binding the galaxies together so that the stars near the outside don't just get flung off into space. Where is that dark matter? What is that dark matter? We know it's there. We can make measurements about what this dark matter's properties are. We haven't been able to create dark matter particles in the lab. You could argue neutrinos are dark matter, but we can't shoehorn neutrinos into our dark matter models and make it work. So there's possibly some other dark matter particle that we've not yet managed to create in the lab. And what about the nature of gravity? Gravity's been difficult to pin down throughout all of this because it's such a weak force compared to the others. We don't even know if gravity acts on that small scale in the same way as we think it acts on the big scale. And on the big scale, we'll use general relativity. But you can't use general relativity on quantized particles. It doesn't work. So particle physics, fascinating subject. And the rabbit hole just goes deeper and deeper and deeper. And it links to every other topic within physics in some way. From the very, very biggest topics, cosmology, our place in the universe, the future of the universe, the past, everything, all the way down to the very smallest scale. When the electron was first discovered, no one could have predicted that we would end up with mobile phones using electronics. No one could have predicted that we'd be able to stream video to each other through YouTube. It didn't take very long before we worked it out. I wonder just how much we are going to discover because of particle physics and delving deeper and deeper that has a direct impact on humanity as a whole. It's a good time to be a physicist. Thank you.